Suppose we have a region S in UVW space, and we take an element in this region, being a finite element, with a finite length of delta U in the U direction, delta V along the V direction, and delta W along the W direction. And every point in a region is transformed one-to-one into the region V in XYZ space. And here we also have a single finite element in V. So each point in region S has coordinates U, V and W, and each point in XYZ space has coordinates X, Y and Z. So the transformation takes inputs U, V and W and maps each point in S to exactly one point in V. So taking the inverse of the transformation function gives us back our point in UVW space. So if we take a position vector to this back corner point of our element, which corresponds to this corner point of our element in S, then we can write the position vector, which is a function of U, V and W, as the X coordinate being a function of U, V and W in the I direction, plus the Y coordinate, which is also a function of U, V and W in the J direction, plus a Z coordinate being a function of U, V and W in the K direction. And now if we take the partial of R with respect to U, so we're holding V and W fixed, we have the partial of X with respect to U in the I direction, plus the partial of Y with respect to U in the J direction, plus the partial of Z with respect to U in the K direction. So essentially, we're walking along the U direction. So this edge corresponds to this edge of our element in V. So therefore this is the tangent vector to this curve at every point along the curve. So this is what it looks like at our corner point. And taking the partial of R with respect to V, we get a similar expression. So we're holding U and W fixed, so we get the partial of X with respect to V in the I direction, plus the partial of Y with respect to V in the J direction, and the partial of Z with respect to V in the K direction. So essentially, in holding U and W fixed, we're walking along this edge from the corner point in the V direction. So this edge corresponds to this curve of our element in V. So the partial of R with respect to V gives the tangent vector to this curve. And similarly, if we take the partial of R with respect to W, we get the partial of X with respect to W in the I direction, plus the partial of Y with respect to W in the J direction, plus the partial of Z with respect to W in the K direction. So in this case, we're walking along this edge in the W direction, which corresponds to this edge in V space. So we have another tangent vector to this curve at our corner point, which looks something like this. Now if we multiply our first tangent vector by the scalar delta U, then we're walking along this vector by an amount delta U. So our tangent vector, scaled by delta U, looks something like this. And similarly, scaling the partial of R with respect to V by delta V, so we walk along this edge by an amount delta V. So therefore our scaled tangent vector looks something like this at this point. And similarly, walking in a direction of W, an amount delta W gives us our scaled tangent vector that looks something like this. So essentially what we're doing is approximating this element by a parallelepiped. So these three vectors form that parallelepiped. So taking the cross product between these two vectors forms a parallelogram, which gives a vector pointing out of its plane. And then taking the dot product between the resultant vector and this tangent vector gives us the volume of this parallelepiped. So it's going to look something like this. So that's our approximation to the volume of our element. So what we have is the volume of the small element is approximately the cross product between these two tangent vectors. So we have the partial of r with respect to u by delta u crossed with the partial of r with respect to v by delta v, and then taking the dot product with that third tangent vector being the partial of r with respect to w by delta w gives our volume approximation of the arbitrary element as a parallelepiped. And then using the properties of the cross product and the dot product, we can factor out the scalars delta u and delta v. So what we have is delta u, delta v, and delta w. So this here is the volume of our element in S space, which we'll call delta v naught. And this here is the Jacobian of our transformation from UVW space to XYZ space. So in the limit, as delta U and delta V and delta W tend to 0, so the volume of our element tends to 0, and what we get is dV is the Jacobian of our transformation, where we'll take the absolute value to ensure we get a positive volume by du, dv, dw. So recall we can write this scalar triple product in determinant form. So we can write the Jacobian as the determinant. We're in the first row. We have the partial of x with respect to u and v and w. And in the second row, we have the partial of y with respect to u, v and w. And in the final row, we have the partial of z with respect to u, the partial of z with respect to v, and the partial of z with respect to w. And this form of the Jacobian can be obtained by expanding this scalar triple product and doing a bit of algebra. And I'll let you verify this as an exercise. So therefore the triple integral of our function in XYZ space, so we integrate over the region V with respect to x, y and z, can be transformed to an integral of our function over the region in UVW space. So we have the triple integral of our function of x being a function of u, v and w, and y also a function of u, v and w, and z which is also a function of u, v and w, and that's multiplied by the absolute value of the Jacobian, and we'll just move this across a bit. And the integral is evaluated over u, v and w. So we're integrating our function over the region S. So essentially, we can transform a more difficult integral over the region V in XYZ space to a simpler integral over the region S in UVW space. And we'll see this in examples. Find the Jacobian of the transformation from Cartesian rho phi theta space to Cartesian xyz space. So effectively a rectangular prism gets transformed into a spherical wedge. So to relate the point with coordinates rho, phi and theta to a point in xyz space having coordinates x, y and z, we can use a spherical coordinate transformation. So here we see that the left face gets mapped to the left face here, the top face to this top face, and so on. And this corner point gets mapped to this corner point. So we have the distance rho from the origin, and that's at an angle phi from the vertical axis, and we can project this line onto the xy plane. So this projected line is at an angle theta from the x-axis. So we can relate x to rho, phi and theta by recognizing the length of this projected line is rho sine phi. So that's the length of this line. So this forms a right triangle with the x-axis. So taking the cosine of theta gives the x coordinate. And similarly y is rho sine phi, which is the length of this line, and sine theta gives the y coordinate. And z is equal to rho cosine phi. So that gives this vertical length over here. And now we can find the Jacobian of the transformation from rho phi theta space, noting it's a Cartesian space, to xyz space. So we can write this in determinant form. So taking the partial of x with respect to rho, we get sine phi cosine theta, and the partial of x with respect to phi gives rho cosine phi cosine theta, and the partial of x with respect to theta gives minus rho sine phi sine theta. And then taking the partial of y with respect to rho, we get sine phi sine theta, and the partial of y with respect to phi gives rho cosine phi sine theta, and the partial of y with respect to theta gives rho sine phi cosine theta, and the partial of z with respect to rho gives cosine phi, and the partial of z with respect to phi gives minus rho sine phi, and the partial of z with respect to theta is 0. And now we can evaluate the determinant. So we'll select the third column to evaluate the determinant. And you can select either row or column. So we start with this entry being minus rho sine phi sine theta, and multiply it by the determinant of the minor matrix consisting of these entries, being the entries that are not in the same row and same column as this entry. So multiplying the cross terms, we get minus rho sine squared phi sine theta, and minus this term by this term, which is rho cosine squared phi sine theta. And then we subtract this term, so we have minus rho sine phi cosine theta, and that's multiplied by the determinant of the minor consisting of the entries that are not in the same row and same column as this entry. So that will be these two and these two entries. So we multiply the cross terms, so that's minus rho sine squared phi, cosine theta, and then minus this term by this term, which is rho by cosine squared phi, cosine theta. And then we add this term being 0, multiply by the determinant of the minor, with these entries which are not in the same row and same column as this entry. But 0 multiplied by the determinant of this minor gives 0. So doing a bit of algebra, we get minus rho, sine phi, sine theta, and we have minus rho by sine theta, which we factor out, and that's multiplied by sine squared phi plus cosine squared phi, which is 1. And then we have minus rho sine phi, cosine theta, and we factor out minus rho cosine theta. So that's multiplied by sine squared phi plus cosine squared phi, which is 1 by the trig identity. So what we get is minus rho by minus rho, which is rho squared, and we factor out sine phi. So that gives sine squared theta plus cosine squared theta, which is 1 by the trig identity. So the Jacobian of our transformation from rho phi theta space, being a Cartesian space, to the xyz Cartesian space is rho squared sine phi. So essentially we can write the triple integral of a function of x, y, and z over region V, being with respect to the Cartesian coordinates x, y, and z, as an integral of a function of rho phi and theta by the Jacobian over the region S, being with respect to rho, phi, and theta. Evaluate the integral by applying the given transformation. So from our limits of integration, we're integrating from x equals y. So this is a plane or cylinder with a linear base that passes through the origin. And we're integrating from y equals 0 to 3. And z equals 0 to 2. So the base of the cylinder looks something like this. And it extends up to z equals 2. And our upper limit of integration gives x is equal to y plus 3, or y is equal to x minus 3. And we're integrating from y equals 0 to 3. So when x equals 3, y is 0. And when x equals 6, y is equal to 3. So the bases of these two cylinders have the same slope. And the planes have the same height from z equals 0 to 2. So this front plane looks something like this. So this here is our region of integration. And now we can translate this region into UVW space by substituting y is equal to v in this equation and solving for x. So that gives x is 3u plus v. And we have y is equal to v and z is equal to 2w. So for this back boundary, we had x equals y. So when x is equal to y, we equate these two equations. So that gives a boundary plane at u equals 0. So that looks something like this. And for this front plane, we had x is equal to y plus 3. So what we have is 3u plus v is equal to y plus 3, which is v plus 3. And therefore the v's cancel, and we get another plane at u equals 1. So that looks something like this. And for this side boundary plane, at y is equal to 3, we get another plane at v equals 3. And for this boundary plane, at y equals 0, from this equation we have v equals 0. So that's another boundary plane at v equals 0. And for this top plane, at z equals 2, when z equals 2, we have another plane at w equals 1. And for this bottom plane, at z equals 0, we get another plane at w equals 0. So these give our limits of integration over the region in UVW space. And now we can evaluate the Jacobian of our transformation from UVW space to XYZ space. So we have the partial of x with respect to u, the partial of x with respect to v, and the partial of x with respect to w is 0. And the partial of y with respect to u is 0, and with respect to v is 1, and with respect to w is 0, and the partial of z with respect to u is 0, with respect to v is 0, and with respect to w is 2. So our determinant is 3 multiplied by 1 by 2, which is 2, minus 0 by 0, and minus 1 by 0 by 2 minus 0 by 0, which is 0, and plus 0 by 0 by 0, minus 1 by 0, which is 0. So that gives a Jacobian of 6. Which means the volume of the parallelepiped in XYZ space is 6 times as large as the cube in UVW space. Now let's move this over here and write our transformed integral over here. So we have the triple integral of our function. So we make the substitution y is equal to v, and u is equal to x minus y on 3, plus z on 2, which is w, and we multiply by the Jacobian, which is 6, and we first integrate over u from u equals 0 to 1, and then we'll integrate over v from v equals 0 to 3, and then over w from w equals 0 to 1. So let's evaluate our integral over here. So we'll take the Jacobian, being a constant, outside the integral, and integrate over u first. So we have v e to the u plus wu evaluated at 0 and 1, which gives ve plus w minus v minus 0. And then we integrate this over v from v equals 0 to v equals 3. So what we get is v squared on 2 by e plus wv minus v squared on 2 evaluated at v equals 0 and v equals 3. So that gives 9e on 2 plus 3w minus 9 on 2, and the remaining terms evaluate to 0. And then finally, we integrate over w from w equals 0 to 1 and multiply by 6. So that gives 9e on 2 by w plus 3w squared on 2 minus 9 on 2w. Evaluated at 0 and 1. And that's multiplied by the Jacobian. So what we get is 6 by 9e on 2 plus 3 on 2 minus 9 on 2. So factoring out the 2, we get 3 by 9e minus 6. Or we can factor out another 3. So we get 9 by 3e minus 2. Find the volume of the ellipsoid using the given transformation. So if we substitute for x, y and z, we get u squared plus v squared plus w squared is equal to 1. And the Jacobian for our transformation from UVW space to XYZ space is the determinant of the Jacobian matrix, which has the entries being the partial of x with respect to u and the partial of x with respect to v, and with respect to w is 0. And the partial of y with respect to u is 0, with respect to v is b, and with respect to w is 0. And the partial of z with respect to u is 0, with respect to v is 0, and with respect to w is c. So the determinant of the Jacobian matrix gives the Jacobian of a multiplied by b multiplied by c, being the radii of the ellipsoid. So we have our integral in Cartesian coordinates over the volume of the ellipsoid. So we integrate with respect to x, y and z, and we transform this into our integral over our region in UVW space, which is a sphere of radius 1. So that's the integral over the region in UVW space, and we have the Jacobian being a, b and c, and we integrate over u, v and w. And given our region in UVW space is a sphere, and our Jacobian is constant, we take the Jacobian outside the integral, and we know the volume of a sphere of radius 1 is 4 pi on 3 by 1 cubed. So therefore the volume of our ellipsoid is 4 pi on 3 by the radii of the ellipsoid. And you could have evaluated this integral by using spherical polar coordinates, which will give you the same result.